Okay, ladies and gentlemen, the time is 12:15, so good afternoon. I am Usama, one of the early stage researchers in the RIBES project and a PhD candidate at the very university at Politecnico di Torino. I will talk to you about the PhD project that I carried out here. The title that I've chosen is called Fish in Motion. We'll talk about some methodologies, some advancements, and then some scientific insights relative to the fish swimming performance. So I spent quite some time thinking about what should I put as my first slide to start with a very basic building block. And I asked myself the question, what is the most fundamental trait of a fish? Like, what is the most basic thing that a fish does? And I said, it is to swim. A fish swims. It is as simple as that. But it is through swimming that a fish is able to migrate short or long distances. It is through swimming that a fish is able to choose the habitat. It is through swimming that a fish is able to reproduce and survive. And again, it is through swimming that it is able to have the predator-prey interactions, and so on. But where is the problem, basically? So the problem is that when we build this, and this, and this, and this beautiful structure, the fish doesn't like it. So what's the solution? Well, one of the solutions, as we have talked over the couple of presentations yesterday and today, is to build fishways. But it is extremely important that before we design the fishways, we must know the fish swimming abilities, which in other words mean we need to know that how long in time and how far in distance a fish can swim at a given flow velocity or at given flow conditions. So how do we do that? Historically, the people have been calling it fish swimming performance or abilities or capabilities, and there are different methodologies that we adopt in order to estimate the fish swimming performance. Some of them I listed here are fixed velocity, increasing velocity, volitional swim test. As apparent from the name, in the fixed velocity, you expose the fish to a fixed velocity until it cannot swim anymore. At the increasing velocity, you keep increasing the velocity until it cannot swim anymore. And in the volitional swim test, you allow the fish to swim at its desired velocity, allow the fish to enter or not enter as it may like. Now, based on those tests, either directly or indirectly, you measure the time to fatigue. And again, historically, people or researchers have been classifying the time to fatigue into three different modes, called burst swimming, when it swims for less than 20 seconds, prolonged swimming, where it can manage to swim up to 200 minutes, and sustained swimming, where theoretically it can swim forever, basically. This is just a video of a fish to show you how it looks like a fish swimming in a flume. This is our flume that I used over the 3 years of my PhD. It's a fish swimming. This is Vairone, the Italian riffle days. And it's like exploring the flume in the habituation period where the velocity is very low, so it can swim and explore the area and get used to the environment. Now, during my PhD, I basically focused on two different things. One was the methodology, and the other was more generalized insights, trying to find some relations where we can advance on the scientific fronts. So I'm going to talk about both of these. But before I go into that, I want to tell you the efforts that we made during these 3 years. We studied 5 freshwater fish. Italian riffle days, we tested 240 fish. Common minnow, we tested 162 fish. European bitterling, we tested 90 fish. North Italian roach, we tested 217 fish. And common bleak, we tested 82 fish. Ladies and gentlemen, it's a total of 791 successful fish swimming trials. And we had a success rate of around 73%, which means we tested over 1,000 fish in these 3 years, one fish at a time. It's a hell lot of work. Now, how did we test it? So we used the fixed velocity protocol. I just want to go through it briefly to tell you how it works. You take a fish from a tank where it is resting. We call it holding tank. You insert the fish in the flume, which has a certain length. You allow the fish to habituate, as you saw in the video, at a low velocity. You increase the velocity to the test velocity. You record the time a fish swims at the test velocity. When it stops swimming, you take it out, you measure its length, mass, whatever you need, and that's the end, and you keep repeating it. But there are many things if you go into the detail. For example, when you insert the fish in the flume, when I say with a certain length, similarly habituate at a low velocity for a certain time, and record the time before it fatigues, there are questions. Does the length matters? Does the time of habituation matters? And what is fatigue basically? Like, how do you define if it has stopped swimming, that's it, or do you want to nudge it, do you want to push it and see if it can swim more? So many questions, and there are many more questions basically that are yet to be explored, but these are the three that I studied in my PhD. So for the part one, about the flume length and different fatigue definitions, I tested Italian riffle days. It was the first year of my PhD where we tried to study two different types of fatigue definitions that have been used in literature. Three different flume lengths. We tested 15, 30, and 100 centimeter, a small fish of 5 centimeter at two different velocities, which we call low and high velocity. And these are the results. Complicated graphs, I'll just tell you the nudge, like the gist, which is that at high velocity, there is nothing much, like there is only so much that a fish can do. So it doesn't matter the fatigue definition, it doesn't matter the length of the flume. A fish can only swim a little bit at high velocity, so it doesn't matter. But at low velocity, if you use one definition of the fatigue or you use the other definition of the fatigue, the effect of the flume length kicks in. So it's extremely important that the people who study prolonged swimming or sustained swimming to take into account what is the length or the cross-section area or the geometry of the flume length to see that if the results are how reliable. And this is what we found in our results. But yet again, we tested one species, we tested like a limited number of fish. You can test a lot to verify maybe there are some other important things that we were not able to test in our protocol. About the habituation time, it's also referred to as acclimation time, conditioning time, settlement time, different terminologies that are used. It's a time that you allow the fish to recuperate before you actually start the test. So we tested North Italian roach for this one, again a small fish. We tested at a high velocity, which is the burst swimming. We tested 35 fish at that velocity, but for 3 different treatments. And what we did was that we gave different time to the fish to habituate. One treatment is 0.5, which is 30 seconds. Practically, it's no time, basically. In the other treatment, we allowed the fish to habituate for 5 minutes and then started the testing velocity. And in another treatment, we gave 20 minutes to see if there is an effect of time on the performance that you then measure. The results, very important and interesting, that when you give very little time, which here is 0.5, which is basically 30 seconds, out of 35, only 7 fish were able to swim. So the success rate was 20%, which is very low. So not recommended. You must give habituation time. However, if you give 5 minutes or 20 minutes, the success rate is a bit different. There is around 10, 11% of difference, but the performance is not much different. But like I said, I tested a lot of fish. Had I given 5 minutes or 20 minutes, I would have saved 6,000 minutes of my lifetime. And the results would have still been more or less the same, statistically speaking, because this is all based on statistics. So it's extremely important to give habituation time, but perhaps 5 minutes is enough, but at least for the fish species that we tested, or for small fish. Maybe for the bigger fish it differs. Then about the behavior, we found out that if the fish is swimming in the flume, when you increase the velocity from habituation to test, it tends to swim worse compared to if the fish was resting during the habituation at the grid, and when you increase the velocity, it starts swimming. Because of course, if the fish is swimming already, it is spending some energy, it goes through transition, spends some energy, while if it was resting, it saves all of that energy, and then it ends up swimming in the testing velocity. So behavior matters a lot. Next thing, we found out that if you force the fish to swim at test velocity, it does worse. So let it do what it wants, because only then it will be doing better compared to the other way around. So what to remember, basically? Number one, fish behavior plays a very important role in performance tests. The definition of fatigue matters. The length of the flume, also overall geometry of the cross-sectional area and the other things matters. Habituation time is very important. But 5 minutes habituation may be sufficient, at least for the small size species. But then again, there is a lot to test to verify if this is also valid for other species and for other lengths. Second part of the PhD, I go something more into generalized insights. So this fatigue time and this velocity test and performance test, what's the goal basically? The goal is this, which is called fatigue curve. It's a simple relation between velocity and time to fatigue. So we build these fatigue curves, and you can see the three different modes: the sustained, the prolonged, and the burst mode. And then based on these, we tend to design our fish ways or the structures that we then need to assist the fish to migrate or for other purposes. But wait, this plot here that you see is simply data plotted. That's it. You do the test, you plot the data, and then you use it for whatever you need actually. And you do it for every species, of course, because for every species the performance is different. But what if we find something that is more or less universal, so that we save a lot of work, a lot of experiments, and that could help us in understanding the fish swimming performance more scientifically? So we propose a theoretical framework based on the drag. We live in a physical world, we are bounded by the physical laws, and so is the case for the fish. Fish faces drag in the water, which is just a resistance to its motion. So when it swims in the water exerts an opposite reaction on the fish, and the fish overcomes that, and only then it is able to swim. And this is a model of the drag force which takes into account the water properties. Here is the density, the dimensions of the fish, length and thickness, the drag coefficient, most challenging one, and the fish water relative speed. The drag coefficient, like I said, is the most difficult one to come up an explanation with, but based on the previous studies and based on some new considerations, thanks to Costa and Vlad, the people who have been behind all these ideas, we thought that there could be three different cases. One, where drag coefficient is independent of Reynolds number. It has been said previously. Then we considered the dependence of drag coefficient on Reynolds number, but considering fish as a rigid body. But of course, fish is not a rigid body, it has undulations. If you take into that account, we come up with this scaling relation between drag force and relative fish water velocity based on the drag coefficient and Reynolds number scaling. So there is a lot of calculation behind that, but I don't want to bore you with that. In any ways, what we find is that based on these three different cases, the exponent of the velocity is limited between 1.73 and 2. And then if you calculate the power that a fish spent per unit time, energy per unit time, it scales with the relative velocity as this. Then of course, over the total time to fatigue for any given fish, the total energy that any fish will spend scales with the relative fish water velocity as this. And of course, if you take an average over a large number of fish samples, we can say that the time to fatigue in burst swimming relates to the fish water relative speed to the power minus beta plus 1, where beta, as I said earlier, based on the relationship between drag force and Reynolds number, is constrained within 1.73 and 2. So we said, okay, this is nice on paper, let's test it. And again, all these species that I tested were then used to validate the theoretical model that we propose. But you have to take into consideration, as Katopodis also mentioned, that there is a huge variability in the data. So even when we do the test, we did not test the exact same velocity, the exact same number of fish, because sometimes it's practically impossible. And it might not also be valid for all the fish. So for example, we were able to test the Italian riffle dace at 4 velocities, but in case of other fish, if we had tested the low velocity, it would not have lied in the burst range. So we were limited by the protocol as well. In any case, this variability is difficult to tackle. But again, we propose this precision index, which we can use as a criteria to test that then the linear regression that we run on our time to fatigue and velocity data, how reliable, how accurate it is. So this simple precision index takes into account the total number of data points for any given fish species and the maximum and minimum mean velocities at which it was tested. When you plot the beta, where beta is basically the coefficient of the velocity that is estimated from the log transformed values of time to fatigue and velocity, and you plot it against the precision index on the horizontal axis, what you see is that as the precision index increases, which in other words mean you have more data, you tested at more velocities, so you have higher precision index, the value of the beta starts to fall on the theoretically predicted range, which was 1.73 to 2. Then again, I tested only 5 species. They are all cyprinids. They are all small species. There is a lot that can be done to validate, to verify if what we are proposing is actually true. And maybe it's true for some species, not for other. For example, it could be that it's true for the migratory species who are used to do or experience long-term, long-duration, long-distance migration, but not so much for the species who don't migrate, let's say. So there is a lot to explore, but the idea we are giving is that there is something that can be done more than just plotting empirical data. So what to remember? We think that our data tends to suggest that the theoretically proposed power law function that we propose between time to fatigue and the mean freshwater relative velocity follows this, this type, where beta results to be within 1.73 and 2, but then again, of course, there is alpha, which is still unknown. But at least in the equation, we have one less variable to know now. And this makes it easier if you want to plot the fish fatigue curve in the burst range. You just need one data point, you have the slope, you can plot the whole line. So it's going to reduce a lot of work in the future if this is actually true. Of course, our experimental data tend to support the relationship that we propose, and there are some universal applications of this relationship. However, more data on different types of species is needed to strengthen the argument that we are proposing. With this, I would like to say a special thanks to the people who have made my PhD possible. Andrea in the lab, Roberto Bosi in the lab helped a lot, Fabio, amazing guy who helped me doing these hundreds of tests. Paolo Loconte provided a lot of fish, Alessandro, very helpful, Alfredo, who is here, and Sofia also. Thanks a lot. And I cannot forget our team, Politecnico. Thanks a lot. Without you guys, it would have been impossible to go through this journey. And with this is the end of my presentation. And I don't know if you guys realize or not, it's also the end of RIBES, basically. Thanks a lot, and if you have any questions, I'm here.